Hey guys, Tom Morgo, Principal Engineer. I'm the ASICs and IOSXE guy. While Mohammed is talking about kind of like strategy and like what is Cisco's bigger plan, specifically the Cisco C9000 smart switches, Kenny's actually showing you the hardware. I get to explain to you guys what's actually in it. So it picks up from everything that they talked about. In fact, the software roadmap and those kind of things. And particularly talking about, it's organized to first talk about the Silicon One ASICs. We've previously introduced Silicon One ASICs, but briefly they said the word NPU 2.0. So this is a new generation specifically built for the campus. Yes, they are being used on Nexus and ASR Cisco 8000 products. But the point of these particular ones is the features and how high scale they are. So it's an entire family of ASICs when we talk about Silicon One, and I have slides, I'll go through it. But these were, if you imagine, like these were built for that feature-rich environment where other ones are just like speeds and feeds. They're fast, but they don't have a lot of tables. These are big tables. Now, I started with this slide. It's almost a recap. When somebody says the C9000 smart switches, it's really going to boil down to these three basic components. And surprise, it's not different components than we've shown previously. It's just like what's different about these. So the ASICs themselves, that's the heart, the actual forwarding capabilities of the switch. And like I said, this new generation of Silicon One ASICs. They've used the term AI multiple times, HyperShield ready, those kind of things. In this initial stage, it really means like application hosting. It's a containerized environment. I can host a small language model there. I can use a machine learning model. I can also, HyperShield is a containerized based distributed firewall. So basically what you're saying is I can host a firewall, I can host AI directly on there. And Kenny kind of already touched on like bigger CPU. He showed you the application hosting slides. Just apply that logic now to an AI SLM or a HyperShield. But the magic, the thing that actually glues it all together is cloud native IOSXE. It's kind of a buzzword. Obviously, we've had IOSXE for a very long time, but the last thing kind of Kenny was talking about where it, he said unified platform, unified software, and it just naturally would open a tunnel to Meraki dashboard. It would naturally open a TLS tunnel to Catalyst Center. So hence the term cloud native. It's automatically there. You don't have to like get a special boot or have to issue some special commands and so on, right? Now, it's kind of a wordy slide. I'm not going to belabor the point. The reason I added this here was this is not Sean's slide. This is not even the Cisco 9000 series slide. This is from our Cisco ASIC group, our central ASIC group, otherwise known as CAG. So work very closely with them, and sort of the things that we talked about, like why did Cisco even move to this new series of ASICs? Speeds and feeds is an easy one. Obviously, we need that. But in the campus enterprise environment, it is very much about like things like adaptable tables, being able to change the number of MAC addresses I have or change the number of access control entries. Kenny talked briefly about NetFlow and those kind of things. So it's very much for this new generation about features. I'm not going to read all these off, but talking about the native encryption. So that means specifically things like MACsec, IPsec, cooked into the chip, right? Now this is a spec sheet. I don't expect anybody to memorize this, but I thought we'd have a good nerdy one. You'll see again, I used that NPU 2.0 to signify that, hey, this is a brand new generation, like the way the processing unit works. And you've heard Kenny talk about like kind of the bandwidth capabilities, talking about the greater scale. And I'm going to go into these in detail, but I just wanted to kind of see it like a spec sheet, like, wow, the 9350, the fixed class doing 256,000 routes. And then he mentioned like 2 million routes on the 9610 coming from these ASICs. And the other key thing is that it is common between them. That's even why I threw in that Cisco ASIC slide. It's like whether it's a Cisco C9000 switch, whether it's a Nexus, whether it's a service provider, all of these are common attributes with a common software development kit. Okay. Now, this is kind of a long one, so the opening one is precisely that. I'm not going to list off all the things. What I really want you guys to see is kind of the high bullets, that common architecture, right? Whole bunch, and this is also true with the previous generation. What this slide's trying to do is kind of show you what's different. What's the new thing I'm getting with this A100 and K100. We had longest prefix match. Longest prefix match is your routing table, that 2 million routes, 256,000 routes. So it's already there, right? But what here is the efficiency. How do I actually pack the individual route entries into it? It depends on how good the memory is, but if it's not very good, you'll wind up with an inefficient program. You'll get like 70% out of it, right? This gets you to beyond 90%. So when I say 2 million, it's like you're actually getting 2 million routes out of it, right? Exact match, it means like I have to match every single bit, right? But this is where your MAC addresses, your ARP, things like SGTs. We're very big on this fabric and group-based policy. This is where I store the SGTs. So the bigger this table is, so it's newer and larger, significantly large. So in the K100, for example, it's a 1.2 million entries. So that's how I can have massive MAC address scale. I can have massive SGT scale and so on. Now, the real money shot, the thing I want you guys all to kind of remember, it's a new acronym, is HCAM, okay? And it's really, it is a TCAM, and it's the thing right here at the first bullet. It's a hash-based algorithmic TCAM. All right, that's some fancy words. What we realized is, and I have a slide on exactly this, that, hey, TCAMs are very, very expensive. But the traditional types of memory like SRAM, DRAM, they're not that expensive. What if I put them together and bring you guys back to massive ACL and NetFlow scale, right? These are like the critical sort of campus things that people care about. I do have a dedicated slide on this. And I'll pause there. Does that kind of hit home?
Yes.
Okay.
I've had it in an earlier session that I took. I keep wanting to think of TCAM in this instance as almost like an index for the bigger memory space.
It is. And so I have a slide on HCAM itself in which I'll talk about it. But at the end of the day, it is coming down to how do I get into that memory? How do I find that? And in the TCAM case, it is index based. Okay, so, and these are all kind of table stakes. This is normal routing and switching stuff. You got to have routes, you got to have MAC addresses, and you got to have security ACLs and those kind of things, right? Well, other things, we've had this in the UADP ASICs in the past, but had not had this previously on Silicon One. So even the first generation Silicon One we added, that same HCAM is now giving you that much larger hash-based memory is also being used for hardware-based NetFlow. So it's the return to hardware NetFlow at these kind of speeds. That's one of the key items. We mentioned briefly data encryption. So this is line rate MACsec, and like I said, that's not unique to UADP, but it is the first time it's come to Silicon One. So now all these new generation of Silicon One ASICs will have this built-in MACsec and IPsec. That's the takeaway. Things like PTP, audio-video bridging. Mohammed talked briefly about latency and those kind of things. So this is also baked into the chip. You guys don't have to memorize all these things and just trying to really trying to drive it home. This isn't just your grandpa's speeds and feeds chip. This was really, really built for enterprise features. Advanced QoS, counters. It may sound weird, but you have all these wonderful capabilities. You better have a counter there, and having super flexible and millions of counters that can be programmed based on whatever application you're running on the switch. And this one's also kind of a weird one. It seems like it's weird. The first generation actually was built for 400 gig. That was one of the items that was discussed. But because it was built for 400 gig, it was not built for 1 gig. But the new A100 and K100 can go all the way down to 10 meg half duplex, from 400 gig to 10 meg half duplex.
One of the slides I was looking for earlier, because yes, we still have equipment that's that stupid.
Yes.
Projectors.
Hmm?
Projectors.
Projectors,
You're not
sensors,
thinking that, but printers and phones.
I would say printers.
Yeah. So it seems kind of silly, but I'm like, no, I have to add that point to it. Okay. I promised I'd have this HCAM, because then this was like the star of the show, if you will, right? It was something new, something that hasn't been done. There's no other chip in the world that's doing this. TCAM, and it's a long story, but TCAM is like infinitely flexible, perfect, precise. It's also very expensive, like actual money, but then the memory space that it takes on the chip, things like thermal, and so not just Cisco or not just Silicon One, but you just look at anything in the industry, other vendors, I won't name them, but the TCAMs are just getting smaller and smaller and smaller. Why is this happening? Well, it's crazy expensive. That's why, right? But in campus, we want really big access control lists. We want that huge NetFlow table. So this was, like I said, like the best of both worlds. I'll give you a reasonably sized 8K TCAM, and then conversely, SRAM is kind of dumb, but it's fast, it's cheap, cool from a cooling perspective. So what if I squish those together? That's where this hash-based, and so I can actually put, if it's a small access list, I can put that small access list in a regular TCAM, it's fine. But what if I have that 10,000 line access list at some kind of like border? What do I do with that? Well, that's what I would put into this SRAM table. So HCAM is the best of both worlds. That's what Silicon One's bringing to you.
Question, Josh.
Yeah.
Diversified. You mentioned in that previous slide that IPv6 took 2 entries. Is that just a math division on trying to divide up that in the address space into those tables?
Yeah, that's a great point, and good catch. So it's the number of bits wide in the memory table. So it is wide enough for source destination address and control of IPv4 addresses, 32 bits. Because IPv6 addresses are 128,
Right.
It runs off the side. So I have to allocate 2 entries for IPv6. So it does mean half scale for v6. But still much, much higher. Now this one, you don't have to memorize. What I wanted to kind of demonstrate is again, that it's kind of both access control and NetFlow. And how Cisco C9000 switches does this is via template. You don't have to do anything for the default template. You just get it out of the box. And when you get it out of the box, we kind of do a 50-50 right now. So if you're looking at like the data sheet, somebody's reading the data sheets, they're posted now. The data sheets are live right this moment. But it's based on this default template. This is what you get out of the box, right? And then we can also do custom SDM. So you can choose, hey, maybe I don't want more NetFlow. Maybe I want more access control list, and you can change that SDM allocation, okay? And then it depends, of course, on the ASIC. So the A100 is a smaller ASIC, thus it has a smaller HCAM, but the architecture is the same. That's what I want you guys to remember. There are just more of the HCAMs on the K100, okay? Buffers, because I'm short on time, I'll just kind of buzz through it. But one of the key things with Silicon One, so this is more conceptual, and this is also true with the other Silicon One ASICs, they will have their own onboard memory. In fact, again, if you look at other vendor chips, they'll have very tiny buffers. It's always a key thing to look at. If you look into the higher classes of chips, they've introduced this high bandwidth memory. It's like saying DDR. It is a actual type of memory that's high bandwidth. And that's the part to remember. But from how do I use it? I can have a small buffer for low latency. I want to get it out of the chip as fast as possible, minimize the latency. But then if I have some slower application, or perhaps it's bursty, it's coming in very rapidly, I can then temporarily put it into this high bandwidth memory. So I'm actually solving both types of QoS solutions with Silicon One.
How do you make the decision what goes into the slow lane and what stays in the fast lane?
So it's very much based on the QoS policy. Then there is a default QoS policy.
We can set a policy.
So you can set your own
that
policy.
says these are prioritized traffic, always fast lane.
100%.
I set a policy that says, you know, fast lane if possible,
That's
fail
right.
to slow lane.
Priority queuing, low latency queuing.
Yeah.
And it's just whatever class you decide to put in there. And even like the little thing at the bottom, it always goes into this, you know, shared memory system, which is the shallow but fast memory first. And then as necessary, so it's only as it hits congestion, then it will send it to HBM.
Got it. So even if you have it configured to be hybrid, if
It's gonna go to
fast lane's
FMS.
available, it's going to use that.
Exactly.
Got it. Yeah.
Exactly.
Is there any cost on that switch? So like, I'm seeing the processing at line rate on packets just flowing through the switch. All of a sudden you fill up your fast lane queue. Like obviously you're going to have some latency added going through the
HCM.
slow lane.
Yes.
Right. But even in making that decision, that seems like a lot of resource to oh, my fast lane's full, I have to flip that over.
Yeah, so it deserves a very long discussion.
Yeah, it's probably more that we cover here.
Yeah, the principle is true. HBM is a little slower. And so normally, even what I tried to draw in the picture, it'd be like, you know, the less interesting traffic, less latency sensitive. So
I get that.
experience that. But you're right, you know, you'd have to be careful.
Go ask your users which traffic's
Yeah.
less important. Yeah.
Your email's stuck in there.
Yeah. Good luck.
Yeah.
But your email can take a few extra microseconds that your high definition video cannot take that. Yeah. Okay. IOSXE, a lot could be said about this. IOSXE itself is not new. Mohammed touched on this. Kenny talked about it a little bit. And this is another animated slide. I'll just go through the high points. So one of the key things, particularly leading up even to the X series, which we introduced a couple years back, was to make everything model driven at a low level infrastructure, software infrastructure. Say, why do I even care about that? We're talking about things like AI, we talk about security. All of these things require data. What does AI, how does it make its decision? It's because it has good data about, link state and particular flows and those kind of things. Where does it get that data? It gets it directly from the switch. And it needs to come in a structured way that it can quickly parse through all these different things to reach its decision, right? So that's the moral of the story. And we've been on that journey for a while. Now, one of the things all three of us have touched on is this unified management and unified software. So it's the same IOSXE running on the Cisco C9000 smart switches, regardless of whether it's operating on the Meraki dashboard, whether it's in Catalyst Center, AI, CLI, APIs. It's a single IOSXE image. Okay, there's no extra boot, no extra change, that kind of thing. Which leads to the next point. We were just talking about cloud native, and I can operate in these different modes: single hardware, single software, and things like AI ML. Because now the way that I'm giving that model-driven telemetry is consistent, and so like the AI behavior in Meraki dashboard is consistent with the AI behavior in Catalyst Center. Now the other fancy one, the takeaway, and Kenny did touch on this, was this next generation stacking capability. If we had more time, I would give you the really long version. I encourage everybody watching to please, this is like one of those really fancy things, to go check out this NG Stackwise. This is really game-changing stuff. But the short version, why I chose this picture, because it kind of gives you the gist. We say things like, Linux kernel, different Linux processes and stuff. If you take a peek at this bootstrap process, BP and cluster manager process, but you'll notice that it's separate. It's different from the normal iOS stack. So anybody that knows Linux means that this process could just die and go away, right? Which happens during software upgrades, In fact, even when you're booting up, the cluster manager comes online first, and then iOS continues to boot up, right? The other thing you'll notice is using those little cylinder symbols, those are databases. Those are Yang models, right? And so the way that, whether it's Catalyst Center, Meraki dashboard, again, that's that model-driven database, and that's actually controlling the cluster, right? And then the last piece that Kenny touched on is that it's standards-based. It's VXLAN, so it doesn't matter. And shortest path first, meaning it's not strictly a ring. The switch treats every interface, whether it's on the back, whether it's on the front, as an Ethernet interface. Okay? And that's where it gets down to the last piece. Mohammed had a little bit of a slide on this one. Things like in-service software upgrades and software patching. That's where it really matters. Like I said, if this guy dies, which can be up to and including a software upgrade, the cluster is still operational. So now I can upgrade the individual switches, the cluster remains online, and this minimizes your impact during a software upgrade.
Question.
Yeah.
Josh from Diversified. What are some of the technical bits that are enabling kind of that microservices architecture between the processor and that layer? You mentioned there's a couple databases in there. It's more of a Linux kernel. Is that just more of a Linux kernel development and that stack development, or is there something specific that's enabled that, maybe like eBPF?
So eBPF is a great point. In fact, I touch it in the next slide.
Okay.
And the other guy said it too, like we should have a whole session just on compensating control.
Right.
And that is, for folks familiar with compensating control and eBPF, that is at the Linux kernel level as I'm making system calls. This itself is actually slightly above that. And that's even why sort of I went through the points the way I did. We've made all of these iOS processes model driven now, right? So they're in a well-structured format, right? And then the extra bit is that cluster manager and Bootstrap that I talked about as a separate Linux process, so that even if something here is disrupted, the cluster itself is not disrupted. One thing that's not cooked in here but is implied is also the application hosting, which is kind of the next slide.
Gotcha.
So it's another example of like protected memory. I can run those in their own memory space. One process dies, the other one's still operational, that kind of stuff. Okay, that's actually a great segue to this one. So, we've always had CPUs. It's not that, we invented the CPU or something like that, but these are latest model Intel x86 CPUs with also, it gets kind of glossed over, much higher DRAM, both faster DRAM and the amount of DRAM that you have available to you, right? So this ultimately, just basic things like how fast is BGP? How fast is spanning tree? But then it also applies to application hosting, right? So in that application framework, and this again, I'm hinting at it. I'm not trying to say anything specific. But again, when somebody talks about, local AI, distributed AI, somebody says HyperShield ready, we're talking about running those in this containerized format. And then the number of cores and how much DRAM is going to be the key factor. That's why it's highlighted in yellow. The other thing Kenny touched on is the link from the ASIC to this CPU is the other big factor. Okay. So, I had touched on the stacking, so I was sort of preempting the slides because of time. But, questions like, what was new? It's this, I said, the cluster manager and Bootstrap process. But what does it mean for me, right? So it's still going to be presented to you as the exact same commands that you have, right? And then it's going to be the benefits from software upgrades. And Kenny was talking about dynamically adding links. In the 9350 discussion, we were talking about, putting them in different combinations, but it's the same, the way that you manage it is the same as it was previously, okay? And the other thing is, it's subtle, but this should resonate with the audience, is before 9350 Stackwise was actually a different thing than 9600 Stackwise Virtual. Like we gave them the same name, but they really were two different things. This next gen Stackwise is the exact same architecture on 9350 as well as the 9610. Okay.
So you've got a bullet point there at the very bottom. You're trying to sneak in there the ISSU. How has it improved? Are we at the point where we can have a healthcare data center, or not a data center, but a closet stack of 10, reboot it and not lose our data plane yet? Or are we still doing a full reboot cycle?
So both of those things, like the answer in there is a bit of both. Anytime you touch the ASIC, like I actually have to change a memory table in an ASIC, it's a hit, right? So I would also like assert to the public audience that there's no such thing as a hitless. It doesn't exist, right? If I touch something anywhere on any device, but having said that, I can minimize it to the maximum that it can be. And particularly in a stack behavior, we're also mixing in things like just ISSU itself. We recently introduced 5 seconds or less extended fast software upgrade, XFSU. So here it's more about, can I run 2 different devices, 2 different switches with different software versions, for example. Like this is one of the benefits of Fabric, for example. But then extending that just now natively into a stacking environment. So like I said, it's a lot of different pieces in there, but it's the normal pieces of ISSU. I'm gonna upgrade the software, minimize the hit to any one member of the stack. And then because of this cluster manager, even if this goes away, the cluster itself never changes. So I don't have to do like a full reboot. It doesn't like go away. Perhaps I'll end it with one point. You shouldn't see link down. That's what I always tell people. Like you should never experience an event where that link perhaps to the wireless access point goes offline. That's like a catastrophic, loss of connectivity. It just means the ASIC didn't send, 4 or 5 packets because it's in the middle of rewriting a data register. But you should never see a link down. That's the magic.
Looking forward to seeing that demo.
Awesome. Okay. I want to go on with this one. I still think it's valuable, but I'll give you the short version. These are the exact same diagrams. They have the same number of devices, the same number of links. The point for the audience, and this already exists, it's to kind of reiterate the point. If you go through and do the math, in a traditional equal cost multipath design, these are 19 unique devices. And also, part of why the slide was first built is like, well, I can do all this now with controllers. Why do I care? The controller's going to do everything. True, but every single one of these is going to open up a tunnel back to the controller. It's going to send syslogs. It's going to send NetFlow. So that is 19 unique sessions, even going to that magical controller. Okay. And then all the individual items, they have to run unique protocols. I have to tune those protocols. And then if you compare that with the exact same topology, same number of devices, same number of links, I have reduced that number to more than half, by more than half of the number of devices that uniquely have to be organized. The other piece I was saving it for the bottom. In this protocol-based equal cost multipath, it's going to be BGP, it's going to be OSPF or spanning tree that makes the decision to reconverge. So when a link dies, stuff happens, right? It then, based on the protocol and whatever timers, will choose the new path, right? That can be in the order of seconds, even minutes in some cases. The real magic of stacking is multi-chassis ether channel, making it a logical interface. And so even how did I reduce the number of peers? Because all these physical links became one port channel interface between you and I. And I don't have to run multiple instances of spanning tree or protocols. And then the real magic is when that link stuff happens, finally dies, it's just an ether channel load balancing. It just takes the remaining traffic and it puts it over the other links. And that is in milliseconds.
I'm just going to call out the elephant in the room. I am not a fan of this diagram at all.
Okay.
The right side is absolutely a valid architectural path, and stacking is not inherently evil, but I don't appreciate or like calling out like leaf spine routed architectures as somehow being bad and stacking being good. And saying
You support both of them.
routing protocols taking minutes to converge is not reality. So I have to call out what I see as being FUD. Please don't use this. I mean, you can talk about the advantages of stacking and whatever, but this is not a cool chart. Sorry.
Okay, that's fair. I mean, in the end, it's going to depend on how you've actually configured it. That's the point I was trying to drive home. I agree with you. And we support both of them. So it's also wasn't a dig on one or the other. It's more a design.
Red X's and green checks, and this is good and you're bad. Like this is a bad diagram.
Okay.
Thanks. I won't say any more.
No worries. No worries. Well, the last thing that I really wanted to go into was picking up from there was the points that Mohammed and Kenny had talked about earlier. Really just kind of the, as the access layer bandwidth is increasing, and the density view of it, right? As Wi-Fi 7 specifically, using multiple uplink ports, the kind of bandwidth that those wireless access points are going to do, and then being able to connect that up from the access layer to the distribution, and finally distribution to core. So those are going to be like the key points where port density and performance, as well as the scale, right? Because I've got more wireless clients connected, so I have more MAC addresses, I have more access control, and those kind of things. Any other key questions on key points?
I actually did have one quick question.
Yeah, please.
With regards to some of the cloud managed capabilities, being able to manage either in Catalyst or in Meraki. What's the minimum code for that? Is that a minimum code requirement?
Great question. And interesting enough, this on IOSXE itself is also available in 1715, starting with 1715. Because the new C9350 and C9610 start with 1718, technically it's 1718.
Okay, so 1718 is the minimum code that
Yes.
on those.
Okay, so this is going to be backpedaled to the 9300.
The management piece of it, unified licensing, unified management, yeah.